non-contextuality, and this is work done, as you already mentioned, with several people. So first is Matthias Guehne, who's a postdoc in my group in Innsbruck, José Portillo and Ana Cabello and Seville, and Jan Åke Larsen is in Linköping in Sweden. Okay, so the outline of my talk is quite short, yes, so the talk is short, I have not much rehearsed, so okay. So I will just first give you a very short introduction to the Becker theorem, just more or less write down some basic inequalities, and then I will talk about classical simulation. So let's start with the Becker theorem, and we'll start more or less with this moment here. So in order to understand this Becker theorem, you more or less need first to define compatibility of measurements. So in general, you can just say that two measurements A and B are compatible if you can measure them simultaneously or in any order and you don't see any disturbance. And you can formulate it more precisely, but I will not do that here. So you can think that of the quantum mechanics, just commuting observables are compatible, but in principle this note is not directly related to quantum mechanics. And once you have defined compatibility of measurements, you can define what non-contextuality means. In this setting, non-contextuality means just the following. So you have a situation that you have three observables, A, B, and C, and you know that A is compatible with B and A is compatible with C. And in this situation, you can of course measure A and B jointly and A and C. And you say now that the theory is non-contextual if it assigns to the measurement A a value, B of A, independently whether you measure B or C at the same time. Yeah, of course you cannot test it because principle A, B, and C might not be measured jointly, but A and B can be measured and B and C, and then the result of A should be independent of C or C. Okay, so now in this context, the Becker theorem just states that models, non-contextual models are in conflict with quantum mechanics. Yeah?
This is okay to ask a question because the first definition says two measurements are compatible if they can be measured simultaneously.
Yes.
It seems I cannot measure measurements. You refer to the word measuring.
Well, actually, yeah, measurement, better to say measurement devices. Observables, you may also say, but observables sounds a little like quantum mechanics. Yeah?
If I accept that, then in the next sentence you say it assigns to A, which is now a measurement device, a value.
Yeah.
I wouldn't assign a value to a measurement device. I perform something, I do something. So
yes, you can see it as a measurement procedure if you wish, and the seal tells you the result of the measurement procedure.
So the value is assigned to what?
Well, in practice, you just make some procedure, you have a black box, and it gives you some result.
I think one has to be very precise about this because you want to learn something that is consistent.
Sure, yeah. Sure. It's just vague definitions. Yeah, so in principle, also what you really mean by saying they can be measured simultaneously or with any disturbance, you have to specify this. This is not so trivial.
But some you don't want to do this.
No, because I don't need it. But at this point, you made us think that you can measure it simultaneously. Actually, we wrote quite recently about it, how you can specify that. But at this point, I will just, for my thing, I will just say, consider commuting observables in quantum mechanics. This is for my talk now, it's completely sufficient. So what do I will? Maybe we can discuss it later, but for my talk, it's not really important. Okay, now this comes Becker theorem, and this is Ernst Becker, and this is Simon Hodgson. So it tells us these modes are in conflict with quantum mechanics. And I will give you a simple example how you can show this. This is known as the Murray-Pierre square. And for that you consider 9 observables, which are labeled here as ABC, small ABC, and alpha delta gamma, in this square. And if you look at them, then you see that all observables in one column or in one row, they commute and are therefore compatible. Yeah, so these obviously commute, these also obviously commute, these also commute, and so on. And if you now take the product of all columns and rows, then, of course, any observer in this total product appears twice. Because any observer appears in one column and in one row. And so the total product will independent of what you assign to the single observers will give you +1. Now, if you consider the same problem in quantum mechanics, then you see that, well, if you take the product of these three observers, this gives you an identity, these three gives you also identity, these also identity, but the last column, the product of these three observers gives you -the identity. So if you measure, or if you consider now this product of these rows and columns, then 5 of them are +1, 1 is a -1, so the total product should be -1. This is obviously a contradiction to this non-contextual model. Of course, in practice, this is maybe something like a logical argument, yeah? This is not very convincing, especially for experimentalists, because they want to have a measurable inequality. And you can translate this into a textual inequality. This goes as follows. I look at the follow-up operator, which is just more or less the first rows of all the rows, then 2 of the columns, and minus the last column. And this term should be understood as a sequence of measurements. Yeah? So I first measure A, then B, then C. And I get, from the first measurement, I get +-1, the second I get a +-1, third also. Then I can get a product of this, which is then also +-1, and I get the expectation value of the product. Okay? And yeah, look at all these 6 terms. And now, I think you believe me, that is, so for classical models, or non-contextual models, you always have this minus sign here, you cannot get rid of it. So the whole thing is bounded by 4. If you do quantum mechanics, well, then the prediction is false. As I told you, this product of observers is just an identity matrix. And here you get minus identity matrix. So all in all, this is minus sign, this cancels. And for all in all, you will have an expectation value of 6. And quantum mechanics predicts this expectation value?
No. I'm sorry, but if you accept quantum mechanics, and Großspecker is automatic, there's no way out of it. You cannot test it experimentally.
No, I will, next time I will tell you what an experiment is.
Yeah, but this is logically impossible, because Großspecker is just a mathematical consequence of the formalism. So if you use Hilbert space formalism, then
Andreas, maybe we should give this to the question.
Sure.
Yes, so we can just discuss later. Maybe more. Okay, so at least quantum mechanics predicts you, if you do this sequential measurements in an experiment, it predicts you a value of 6. And people have done this experiment, and I've talked already on Thursday about it, just give you the value. The value what they found is the value of 5.46, with a 2-ion experiment, and this is a clear violation of the experiment. Okay, so we may now ask the question, is this really surprising? Yeah, so, well, you clearly see a value which you cannot explain with a non-contextual model, but you really have to care. And the point is, what you may ask, couldn't this be explained by a classical mechanism? Of course, if you have some classical mechanism to explain this experiment, it has to be contextual, but still it might be a simple mechanism. And so what you could think of course, is that what happens if I make this measurements in a sequence? What happens if this system I investigate, someone just remembers all the measurements I've made before, and then correspondingly gives me the right answer to give the value of 6 of the Stockholm packet? Of course, this is a possible model, this is contextual. And so the question, what I will talk about just now, is just the question, okay, you can look at this model, but what memory does it require? Of course, one model, what I already told you, is to remember all the measurements, which have been done before, but this may be a little bit wasteful. in the context of better inequalities, but people were looking at how much communication you need to achieve a violation of better inequalities. So, what is now our model? We assume we have a machine which looks like that, and we have more or less 9 possible questions what we can ask. Yeah, these are A, B, C, small a, B, C, I don't get down. Maybe I should write them down because I will always order them. Later I will do some. So always the order of the things is always A, C, because this order of the things will appear later. Always, if I make A, B, C, I may always need this thing in the memory. Okay, so there's a machine. You can answer 9 questions, and it always gives you plus or minus 1. And what does the machine should give you? It should, at the end, it should give you that if you measure one of the columns or rows, for instance, if you measure A, B, C in a sequence, first not this one, this, and this, then the product of the three results should give us a quantum predictive of Merkle pairs. Therefore, the product should be plus 1. Yeah, if you want at some point measure this last column, which should give you minus 1, then, well, press the corresponding box. It should give you this minus 1. And I will assume, discuss this later, there is one machine in which I can press it not as often as I like, but I have only one machine. Okay, so the question is, what is the memory of this machine? And I'm always considering this when I'm talking about memory, something like the RAM. That's an executive memory. Of course, the machine also has to remember its program, so, but this is not the important point. It's also the active memory. Okay, now to be a little bit more precise, we have to define the rules of the game. Yeah? What do you mean? What are the conditions which you have to fulfill? So one first important rule is that the things should be interpreted as measurements. So if I press 2 times the same button, the result should be the same. Yeah? Because otherwise it's not a serious measurement. Then of course, because we play this non-Paris game, we should have all the 6 predictions from the non-Paris square. Yeah, so if we, in our long sequence of questions that we ask, if at some point we ask 3 of this one column in our one row of this non-Paris square, then the product should be the right answer. Yeah, of course, if we somehow measure first A, then B, then gamma, and so on, then there's no restriction on the answers of the machine. But at some point, if you measure gamma, C, for instance, again, then the product should be minus 1. Another thing what we, of course, require is that the observers are compatible as they should be. For instance, if I measure a sequence like A, B, C, A, then the result what I get for the first A and for the fourth A, this one should be the same. Because otherwise I would not have been wrong. And these are the basic assumptions which you really need. You can ask for further constraints if you want to do that. I will discuss later this a little bit. For instance, you can what happens if you have A, C, A, small a, big A. So A, C, small a, big A. Then should the value of A stay the same? This is not so trivial whether you want to assume this or not. Because, well, we can argue we want to assume that because C and small a are compatible with A, so they should not disturb the value. But you can also say, no, I don't want this, because C and A, not all of these 3 things are compatible, mutually compatible, so you cannot measure them simultaneously. But I come later to this. Okay. And you can go further to the end when you want that the machine reproduces all quantum predictions, which of course a lot of predictions you want that. So what for machines do we look at? In fact, we assume the following scheme. So we have a memory which can be in one of k states. And the logarithm of this number k state is the memory what you need. And for any of the memory states, there are 2 tables. Yeah? One table which gives you the answers to all the 9 possible questions. So these are just the values which the machine will give you if in this memory state we ask maybe the question A or B or whatever. And we need a second table, which tells us how we shall update the memory. Yeah? So we also need to table, okay, where we say, okay, now if we have asked the question A, then maybe the memory state should change from 1 to 2 or whatsoever. And this we also have to keep track of. And these things are called mean machines in information theory. Okay, that is not so important. Okay, maybe it's first good if we give you a simple example. Consider the following machine. Yes, these are we have 3 memory states. 1, 2, and 3. And these are the values of the table, so the values of the observables, more or less. And these are the update tables. And now you can ask, well, what would this machine reproduce? So let's start. Maybe we start in memory state 1. Okay, let's assume we measure alpha, which is this thing here below. Now alpha, then we get a plus. And then we look, oh, shall we update the memory? No, there's a 0, we don't have to update. Then let's measure the observable A. We get a plus, but then our update here does, oh, we have to update the memory to stable 2. Okay, now we are here. Then we measure big A, we get a plus, but here there's a 0, we don't have to update. And you can go further, then you measure gamma C, and you see this is the index of the memory just, and you see sometimes it updates the memory, and often it stays the same. And you also see that it, at least in this simple sequence, it does the job that we want. Yeah, for instance, if you measure A, alpha, small a, big A, the product of these 3 is plus. If you measure big B, so big B, beta B, so this one, the product of these 3 is plus. And so, and you can check that this does the job. So, what you can, first you can really prove that this machine doesn't drop. Okay, you better do it by computer, by checking all the possible sequences. And you can also prove that this is the simplest machine. You can prove that a machine with 2 states cannot do that. Another thing is also that this machine fulfills its compatibility conditions. Yeah? For instance, if you measure something like here, what you measure side machine 1, you measure C, B, A, C, which means you measure C, B, A, C, then the memory state changes, but the value of C does not change. As it should be, because the only memory compatible observables. Okay, so why is this optimal? Well, to just prove it by contradiction, in this case it's quite simple. Let's look at the possible tables. Yeah? So there's one table. And we know this table has to have one contradiction to the Merkel condition. Because it's just this is a non-contextual assignment, there must be one contradiction in one file order. You can assume that it's in the third column, and all the entries are plus. There's no restriction of generality. But then, we could, starting from this table, make a sequence like this one, this one, this one. And now we are not allowed to arrive at a contradiction, so the memory state has to change at some point, and you have to jump to a table where this column is okay, where the product of this 3 things is symbolized. So there must be a second table where this sign is okay. But also, in this situation, we could also start with this observer and measure from A this one, then this one, and this one. Then we must also the case that the last column is okay. But this cannot be this one because here this value has flipped and this would be a violation of compatibility. So there must be a third table where first this value is equal to this one and the last column is okay. And this means that you cannot do this 3 memory states. Okay. Let me come to another example. How much time do I have, by the way?
7 minutes.
7 minutes, okay. Because if you look more carefully at the automaton which I presented you, it has some problems. Or, well, it depends what you call it. So it predicts you the following: if you measure C, A, gamma, and C, then the value of C changes. So which means you measure C, A, gamma, and C, and the value of C changes. The point is so, you cannot measure these three observables at the same time, yeah? Because A and gamma are not compatible. So you say, I don't care. This is one way, and then you could use other one before. But you can also argue that, well, A is compatible with C, so it should not change the value of C. And gamma is also compatible with C, so it should not change the value of C. And if you argue like that, then the machine before has a problem. And so this is a little bit a matter of cake. First, quantum mechanics clearly predicts that this should never occur. Yeah? So if you want to obey quantum prediction, then you have a problem. So you can argue whether you like this condition or not, but if you want to incorporate such conditions, then the machine has to look like that. Okay, I'm going to go into details because how it works. But in principle, you get a machine which has now 4 states, and it also fulfills these conditions, and it can also prove that it's optimal. But actually, this time to prove that it's optimal is already a little bit more complicated, so we're not talking about that. But still, you need only 4 states with 2 bits of memory. Yeah, and you may say, okay, I have 2 qubits. Well, I know from the Lego bounds that in 2 qubits I can store 2 bits of classical information. So why is this interesting? The point is, there are other inequalities which are like extension of the Merkel square, where you cannot use it anymore. And they are more or less like a nested version of the Merkel square. And we'll just shortly explain this. The idea how to do that is to look at all possible products of polymorphs. Yeah? For 2 qubits, here there are. And then you can just count which of them are compatible and which are not. Yeah, for instance, if you look here, these are compatible, or this are compatible. You can go further. These are compatible. This off diagonal, which means this, and this is compatible, this is compatible, and so on. Then you can look at the products. You look at the product of all these 3 compatible observables, and they can give you either a +1 or -1. And if you look, in most cases, the product of these 3 things is +1. Yeah, for instance, this times this gives the plus the identity. This times this gives plus the identity. This gives plus the identity. But there are 3 cases where the product is a -1. Yeah, so this product is -1, this product is -1, and this product is also +1. So from this, you can now write down an inequality, which is like an extension of the Merkel square, and where you just take all the positive products minus 3 the negative products. All in all, you have 15 terms. Quantum mechanics predicts you for this inequality value of 50. But in classical models, you can show that you get a value of 12 minus 3, which is 9. Excellent. And this has been recently proposed by Alan Carey. And if you try now to simulate this extended Merkel square, well, then you can argue as following. So in principle, if you look at this Merkel square again, it's just a version of many Merkel squares nested. All in all, there are 10. Yeah? You count there are 10 Merkel squares. And, well, in any context, it appears in 4 of them. And now you can show that if you write down a non-contextual model, a non-contextual assignment to this extended Merkel square, there must be, in one of the 10 Merkel squares you have, there must be 3 contradictions. Yeah? Usually you have only 1, but in this case there must be 1 Merkel square with 3 contradictions. And you can show the following. If you try to write down 4-state automata, which has 3 contradictions in one table, this you cannot do. Yeah, so you can prove that And this proof is unfortunately, but it's in principle brute force. They just try. And unfortunately, but it's several pages, so I don't want to present it. But it's, in principle, it's simple. And what does it show? This shows you that if you want to classically simulate this extended memory pairs inequality, you need more than 2 classical bits as a memory. This is more than memory that you can store into quantum bits as well. Okay, now my time is sync up. Yeah, you can also ask, this is more ongoing work, what happens if you can reset the machine? Yeah, at the moment, I told you always assume one machine, where I can ask a long sequence, but what can happen if I can reset the machine to the initial state? One can show that if you then want to fulfill the compatibility conditions, that this machine needs some randomness. Yeah, but I'm not talk about this so much. Okay, so what I've shown you? Well, I've shown you that you can simulate non-contextuality or quantum contextuality with classical means, but you need some memory. And I've given you, for several cases, I've given you the optimal machine simulating such contextuality effects. There are a lot of open questions, yeah? So, okay, I only considered a small set of quantum predictions which you want to simulate. If the question is, what happens if you want to simulate all perfect correlations of quantum mechanics? Because there are a lot of others. Probably, or we don't know, but in principle it could be that you need already an infinite amount of memory. But we don't know. Another thing is, what is to ask is, this automaton which I presented you, what exactly do they remember? So, it's not really clear. You have this automaton which reproduces the things what you want, but what's its memory state? This is not like, we cannot easily, for instance, like remembering what measurement we make. Yeah, so it's not really clear what the memory is in this automaton. Okay, that's all. Thank you for your attention.
Questions, comments?
Maybe I'm a bit thick, but who were the frogs and the mice supposed to be?
This is not serious.